Okay, so hi. For this video, we will be discussing limits and solve some examples. Okay, so when we say limits, so a limit describes how a function behaves near a point instead of at that point. Okay, so what does this mean? Okay, so it means that the value, okay, so the value of the function near a point. Okay, so when we say near a point, so not exactly at that point, but near that point. Okay, so we will understand that later once we have the illustration. So but for the notation of the limits, so the value of the limit, so let's say that is L, so it is denoted by the limit of the function as the variable approaches to a certain value a. Okay, so it is read as, so this, okay, is read as the limit of f of x as x approaches to a is L. Okay, so notice that again for the limits we only use the value of x, okay, approaches to a certain value. Okay, so not exactly at x is equal to a, but as x approaches to a. Okay, so that is, okay, so that is as described here, near a point. Okay, so what is the value of the function, okay, at it goes near to a certain value a. Okay, so illustration. Okay, so we have here two functions. Okay, so the function of 2x plus 1 and this one 2x squared minus x minus 1 all over x minus 1. Okay, so both, if you graph those two functions, okay, so the graphs will be identical, so just straight lines. Okay, but as you can see, 2x plus 1 is continuous. However, as we can see from this function and our background knowledge in functions and limits, we know that the domain of this function is x is not equal to 1. Okay, so this function is indeterminate, okay, at x is equal to 1. Okay, so that's why we have here, as you can see, we have here the graph of the function, but here we have here a point, an open dot. So this means that at this value, so this is at x is equal to 1. Okay, so the graph, okay, or the function does not exist, okay, at x is equal to 1. Okay, so because if you try to compute, if you substitute at x is equal to 1, so therefore this will become 2 times 1 squared, so that is 2 minus 1 over 1 minus 1, so that will be 0 over 0. Okay, and 0 over 0, 0 divided by 0, that is indeterminate. Okay, so but since this is a limit, okay, problem, so what is the value of this function, okay, as x approaches to, okay, like that, so the value of x approaches to 1. Okay, so although it's not defined at this point, but we can see, okay, from based on the graph, we can see that this is at same with this, because this is identical at x is equal to 1. The value of the function is 3. Okay, so this also, so this is this point, okay, although it's undefined by the function, we can see that the value of the function approaches to 3. Okay, at if x approaches to 1, so either from the left or from the right, so the value of the function approaches to 3. Okay, so that's the difference between functions and limits. Okay, so if we evaluate the function, if we say f of x is equal to 2x squared minus x minus 1 over x minus 1. Okay, so when we say f of 1, so this will become 2 times 1 squared minus 1 minus 1 over 1 minus 1. Okay, so this will become 0 over 0. So this is indeterminate. Okay, indeterminate, so on. Okay, so but using limits, okay, so if we use limits to evaluate this function, so we can see that the limit of 2x squared minus x minus 1 over x minus 1 is equal to 3. Okay, so that's the difference of functions and limits. Okay, so when we say functions, okay, so if we say functions, So that is the value of the function at the given point. So the value of the function at the given point in this example is indeterminate. However, its limit as x approaches, okay, approaches to 1, the value of the limit approaches to 3. Okay? Okay? So the concept of limit shall be used in differential and as well as integral calculus. Okay? So bear that in mind. Okay? So in calculus we will be using limits, okay, instead of functions, because limits, so they can describe the value of the function that ordinary substitution cannot give. Okay? Okay, so some examples in evaluation of limits. So let's solve some problems. Okay, so let us solve these two examples and we'll add one more later maybe. So we'll have number 1, evaluate the limit of 6 plus 4t all over t squared plus 1 as t approaches to negative 3. Okay, so to solve this, although the concept of functions and limits are different, when evaluating limits, what we need to do is just similar with evaluation of functions. Okay, so all we need to do is substitute the value for which the t approaches in the function. Okay, so what we need to do is just substitute. So we have 6 plus 4 times t approaches to negative 3 over t squared. So we'll have negative 3 squared plus 1. Okay, so that will become 6 minus 12 over, so it will become 9 plus 1. So this is 6 over 10, or, sorry, negative 6 over 10, or negative 3/5. Okay, so it's that simple and straightforward. Okay, so next is the limit of 2z squared minus 17z plus 8 all over 8 minus z as z approaches to 8. So similar with what we did in number 1, so all we need to do is substitute. So we have 2 times 8 squared minus 17 times 8 plus 8 over 8 minus 8. So this will become, so using our calculator, so 2 times 8 squared minus 17 times 8 plus 8, we have 0 over 8 minus 8, 0. So this is indeterminate. Okay, so however, so we don't jump into conclusions immediately. Okay, so similarly with what we had in our illustration, okay, so the value of the function is indeterminate at the point, but it has a value for the limit. Okay, so what we can do is we look for ways, okay, to make our function, to simplify our function. See if we can simplify our function first before substituting the value of the limit. Okay, so one way is to factor. So we can factor out the numerator and see if we can simplify the expression. So the numerator is, we have 2z squared minus 17z plus 8. So usually factoring this would be done by trial and error. Okay, so but we'll have this method. So we will multiply the first and the last term. So 2 times 8, the coefficient of the first and the last terms only. So 2 times 8, that is 16. Right? So next is we will factor out 16 such that the sum of the factors is negative 17. So factors of 16, so we can have negative 1 and negative 16. Okay, such that negative 1 times negative 16 is positive 16, and negative 1 plus negative 16 is negative 17. Okay, so therefore we will divide the middle term. We will break down the middle term with coefficients of negative 1 and negative 16. So we will have 2z squared minus z minus 16z plus 8. Okay, as you can see, if we add this, so it will return to the original expression. So but in this way, we can now group the first two terms and the last two terms. So we have, in one group, we have 2z squared minus z, and then plus negative 16z plus 8. Okay, So for the first group, greatest common factor is z. So we can factor out z. So what will remain inside is 2z minus 1. For the second group, we can factor out negative 2, or we don't. Yeah, we should. So we factor out negative 2. So what will remain inside is, negative 8. Greatest common factor. So factoring out negative 8, so what will remain here is positive 2z, and 8 divided by negative 8, so that is negative 1. Okay, so now we have two terms with the greatest common factor of 2z plus 1, 2z minus 1. And if we factor out 2z minus 1, so what will remain in the first term is z, and this is minus 8. Okay, so therefore, rewriting the given, so the limit of 2z squared minus 17z plus 8 over 8 minus z, as z approaches to 8, is equal to, factoring out the numerator, is equal to the limit of, since this is the factor of the numerator, so 2z minus 1 times z minus 8 over 8 minus z, as z approaches to 8. Okay, so as we can see, we can cancel this out. So if we factor out negative 1 from the denominator, so the limit of 2z minus 1 times z minus 8 over, factoring out negative, so this will become negative 8 plus z, okay, or z minus 8, as z approaches to, z approaches to 8. Okay, so we can cancel this out. So therefore, what will remain is the limit of negative 2z minus 1 as z approaches to 8. So we can now substitute 8. So this will become negative 2 times 8 minus 1. So 2 times 8, that is 16, minus 1, that is 15, and then negative outside. So therefore, the value of the limit approaches to negative 15. Okay, so that's it. Okay, so we shouldn't jump directly into conclusions that the value of the limit is indeterminate. Okay, so we see first if we can still simplify the function, okay, so that we can obtain a value for the limit. Okay, so for our, let's have another example, third example. So the limit of okay, so let's have this one. So the limit of the square root of 2x plus 22 minus 4 over x plus 3 as x approaches to negative 3. Okay, so let's try substituting directly the value of negative 3, but as we can see, the denominator later on will become 0, so making the value of this function indeterminate. Okay, so we can skip that step. We can already see that it's indeterminate, so let's just find a way to make this work. Okay, so also in the numerator, so let's see square root of 2 times negative 3 plus 22 minus 4. So the numerator is also 0. Okay, so as you can see, we cannot factor, okay, in here, cannot factor the numerator, but what we can do is we can rationalize the numerator to remove the square root. Okay, so to do that, we should multiply the numerator and the denominator by 2x plus 22, square root of 2x plus 22, and then plus 4. Okay, so with that, we can eliminate the radical sign in the numerator. So the limit of rewriting. So the limit of the square root of 2x plus 22 minus 4 over x plus 3 as x approaches to negative 3. So we can multiply, okay, and divide by square root of 2x plus 22 plus 4 over square root of 2x plus 22 plus 4. Okay, so why did we do that? Again, to eliminate the square root. So recall, in special products, if we have a plus b times a minus b, so it will become a squared minus b squared. Okay, so therefore, if we multiply the numerator, so the limit of it will become, the numerator will now become square root of 2x plus 22 squared minus 4 squared. Okay, so while the denominator will still be x plus 3 times square root of 2x plus 22 plus 4. Okay, so as x approaches to negative 3. Okay, so next we can simplify the numerator. So if we haven't substituted the limit yet, we always we still write the notation for the limit. So limit of, so this will become 2x plus 22 minus 16, right? So because square root squared, so it will eliminate the radical sign, over x plus 3 times square root of 2x plus 22 plus 4. Okay, so make sure always that the vinculum covers all the numerator and the denominator. So next is simplifying. So 2x plus 2x plus 22 minus 16. So 22 minus 16, that is 6. Let's check. Yes, 6. So the limit of, this will now become the limit of 2x plus 6 over x plus 3, and then square root of 2x plus 22, and then plus 4. Okay, so as x approaches to negative 3. And then next, we can factor out the numerator, actually. So greatest common factor is 2. So if you factor out 2 from the numerator, so it will become 2 times x plus 3 over x plus 3, and then square root of 2x plus 22, and then plus 4. Okay, so as x approaches to negative 3. So with that, we can now cancel out x plus 3, and then evaluating the limit, so it will become 2 over square root of 2 times negative 3 plus 22, and then plus 4. So this will now become 2 over, so this is 2 times negative 3 plus 22, 2 times negative 3 plus 22, that is 16. Square root of 16 is 4, so 4 plus 4, so that is 2 over 8 or 1 over 4. Okay, so that's it. Okay, so we have done that by rationalization. Okay, so removing the radical sign of for one of the terms. Okay, so you can also do that rationalization if you can see a radical sign in the denominator. So but basically that's how you do it. Okay, so you apply this special product. Okay, and you must always multiply the numerator and the denominator with the same term. Okay, because as you can see, if the numerator and the denominator are the same, so therefore this here is just equal to, this is equal to 1, right? And anything multiplied by 1, so its value does not change. Okay, So the value is still the same because we have only multiplied it by 1. So although it looks different, okay, so but the values are the same. Okay, so that's it. So good luck with your exercises, and thank you for watching.